what's really interesting also is that they can report the local refractive index by looking at the shift in that scattering peak. And it's very sensitive. You can have up to 500 nanometer change for one refractive index. In order to target them with molecules of interest, we functionalize them, so we decorate them with antibodies. So we've come up with a number of different protocols here. So here we got this linker and the antibody sitting there that came out really low resolution for some reason. But the idea is to decorate these nanoparticles and perhaps send them into the bloodstream. And as they're interacting, they would find these cancer cells and bind to them because I've got that antibody that matches up with an overexpressed receptor. The one that we look at most often is EGFR, or epidermal growth factor receptor. This is a receptor that's overexpressed in cancer because it's what tells the cell to start dividing. So if I've got a cancer cell with a lot of these receptors, it's primed to get the growth factor, and that would initiate cell reproduction. So it's not uncommon to see, especially epithelial cancer, showing a lot of these EGFR receptors. We've done a number of studies with these over the years. My references are probably cut off. I'll describe it. Okay. So we have nanoparticles bound to our cells. These are 4 different cell lines. These are glioblastomas, skin cancers, and a couple of other cell lines, breast cancer. What we did was we showed that our nanoparticle binding compared very favorably with fluorescence imaging. Fluorescence imaging has its problems. Very tough to do quantitatively, but we showed that we got good alignment there, and there was a paper that came out in 2008, the author was Crow, that showed that we had a nice little response. When we're imaging these, we have kind of a unique system. We have this Epi-illumination Darkfield, which is kind of a unique geometry for a Darkfield. What we did was we put an axicon into a beam path, makes this converging cone of light, and we bring it to a focus at the back focal plane of the objective. Light is then reflected, is blocked by an aperture, whereas light that's scattered, also cut off the light image here, makes it right through this aperture here in the center. So we're able to get images of just the backscattered light. And that makes these nanoparticles stand up really bright. So even though they're nanoscale, 10, 20, 40 nanometers in diameter, you're still able to see them using this dark field microscopy approach because they scatter light so brightly at this one particular wave. For the system, again, we're using our super continuum source. We've got great mileage out of these. I've brought a couple of them from titanium, and I've used some ones from NKT. By putting an acousto-optic-tunable filter, you can scan through all these different wavelengths really quickly. This one had 8 channels, 5 nanometers each, and you can sweep through the full data cube here in 4 seconds, 400 to 700 nanometers, and get a hyperspectral cube of all your nanoparticles. And I like to show this one with this sort of nice colors, but this shows multiple different tags bound to the nanoparticles. So here we're looking at gold nanoparticles bound to the HER2 and SKDR3 cells. You can see that the peak is in the green region. Here are nanorods that scatter mostly in the red region, and there we're detecting EGFR in this MPA cell. And then finally we had these 100 nanometer silver nanospheres, and they were going after insulin-like growth factor in this A549 cell. So, the author there is Kevin Siegel, who was 2014, and NSF highlighted this at one point. One of the things we did with these nanoparticles was applying them to flow cytometry. So in flow cytometry, very often what you'll do is you'll have a fluorescent tag that you bind to cells to let you know if you've got a specific molecule there present. But what we realized is that if we just pulled the filter out and just looked at the scattering of this laser light using the side scatter filter on a flow cytometer, we could actually pick those up really easily. So we bound them to our nanoparticles, and again, we found just as good as the fluorescent tag. This was Crow, showed up in flow cytometry A. So I bring up the gold nanoparticles because what we've been doing recently is combining these gold nanoparticles with our phase imaging to understand how we can see additional molecules that may be more revealing. So our work's been focusing on improving the detection of these nanoparticles using interferometric means and providing this additional information. So one way you can go after nanoparticles is by taking advantage of their photothermal nature. So if you hit these nanoparticles with pulse, they actually heat up very quickly, but very locally. And if I'm looking with a phase microscope, I can see those. This is something that we invented. Boyer did this back in 2002. In this example, this is able to visualize 80 and 10 nanometer gold nanoparticles, but the latex one had no contrast. SNR was pretty limited though, so if you wanted to base a diagnostic on this or do anything useful, it was a tough road, right? SNR of 2.5 to 10, size dependent, very tough to get a robust measurement. One avenue we explored was photothermal OCT, and this was the idea to use the phase sensitivity of optical coherence tomography to be able to pick up these nanoparticles. So in this approach, the pump beam was used to photothermally excite the nanoparticles at 532. It was chopped on and off at a pretty slow rate, 25 hertz. And then what you actually see is that the phase signal oscillates in time. If I do a Fourier transform, I'm able to get good signal here. SNR is pretty good. It's on the order of 10, so it's good to see. I should point out that this was work that was done by MOS Adam Wax, collaborated with Joe Isaac's group back in 2010. In this approach, she actually did extend it to looking at cells. So this is the GFR expression using the photothermal OCT. Couldn't really see individual particles, but rather were characterized here by a limit of detection, where the SNR was about 1. The first demonstration was about 14 parts per million. Recent work from her group, MOS Adam, which was in 2012, moved this down to 1.2 parts per million, so it's 7.5 picomolar. Not able to pick up individual cells, individual nanoparticles, but could see really, aggregations. So we wanted to see how far we could push photothermal OCT to do single nanoparticle tracking. So what we realized was that, first of all, that modulation approach, you have to integrate over several cycles. So it took about a second for each one. Very slow. Not only that, but as you heated the nanoparticles, you actually lost sensitivity. So if I had a cold nanoparticle and I hit it, there's a sharp change in temperature. But after the third or fourth cycle, I'm no longer seeing that change in temperature. And I can see this here when I look at how I excite my nanoparticles over time. My first pulse really increases that phase a lot. When I get up there to the top, it's maybe, a quarter of the amount of the phase change. So we came up with this idea of doing single pulse excitation. So we would hit it with one pulse and then look at how the phase would rise and fall for each of those. It improved this down. We were able to get down to 1 to 3 millisecond acquisition, but it was tough to keep the same sensitivity. So we got down to about 38 picomolar at an SNR of 10. So it was a way to improve it, but perhaps did not get us the sensitivity that we were looking for. This was done by in my lab in 2012. Another approach was to use spectroscopic OCT. This is another project that I'm not telling you about, but this is a technique that we've used widely in my lab. If I have a broad bandwidth source in optical coherence tomography, I can actually subdivide it and look at different spectral bands. So the question was, could we just see the absorption? And the answer was yes, we could. We made these 3D cell constructs, stuck some nanoparticles in them. We had pretty short acquisitions, it was 40 milliseconds, so that's acceptable for an imaging modality. The limit of detection was much higher, it was about 0.5 nanomolar. We could go to longer integration time, maybe get down to 10 picomolar, but we realized this wasn't really the path we wanted to get down to at these fast measurements. So we began instead to look at photothermal imaging with phase. So we were doing our quantitative phase imaging of cells, and those are the images on the top. Sorry, those are the images on the bottom. And then what I have on the top are grayscale images of these phase images with the photothermal signal laid on top of it. So we would take an image of our cells, whack it with a 532 pulse so we get a phase change, and then take another image. And then the green I'm showing here are the differential images. Just to give you an idea what the beam is encircled by the red. So you can see the cells that are inside the beam light up, the ones that are outside the beam do not. We got really high SNR on this with a very short acquisition time, 103. But we didn't quite get down to that single nanoparticle detection that we were going for. One of the issues that we came up with here was that, just like in the OCT, once I started heating it, that signal stuck around for a while. We saw the same thing here. So what would happen is we hit it with a pulse, and there was actually this long thermal tail that would come off. You actually have to wait for it to cool all the way back down before you can compare it to your reference again. And so we came up against a wall where we were trying to average these more to get better SNR, but it would just be limited because your background would be low. In this modality, really what we're going for is do I need to see individual nanoparticles, or do I need to see individual cells that express these nanoparticles beyond some level? And so here we started really changing our idea, saying, well, what if I just wanted to identify cells? So we took a look at one other type of technique, which was using the photoacoustic approach. So in photoacoustic, same idea. You're hitting it with an optical pulse, and instead of looking at the thermal change, you're actually listening to the cells and looking for the acoustic signal based on the model. People do photoacoustic tomography, and it's generally a pretty complex system. So our real innovation was to come up with this very low-cost, easy detector. So this is just a ring ceramic, stuck wire on there, maybe 6 millimeters in diameter. It costs under $10 to make. All right, so we put this on top of our cells. We went ahead, we did a phase image, and then we whacked it with a pulse, and we got a low-resolution photoacoustic image. It takes a little bit more time to get, but we do get pretty good SNR. And one of the C gets down to the idea if I just want to identify that cell with a single hot pixel, then I can do a low-resolution scan and get it done in a fairly reasonable amount of time. So it's a bit slower due to scanning, but it's a new approach, and we're going to explore it further to see if it's something we can incorporate into the chip format, where we can just identify individual cells, perhaps. So to sum up, I've shown you how nanoscale information can be obtained for live cells using these optical techniques. Our quantitative phase imaging can reveal changes in structure and function due to disease. We've used nanoparticles as molecular tags to reveal the presence and dynamics of the cell receptors. And the combinations of this approach could potentially yield a low-cost diagnostic that's suitable for clinical use. I'd like to finish up by thanking members of my group that have participated in this. The work I've shown here has been the work of Matt Reinhardt, Abby Scheinfeld, Hansen Clark, and Sandy Kim. Nadia Shackett was professor I mentioned, was moved on to other things at this point. This is some of our other alumni here. And then our collaborators on this project, in particular, Marilyn Teller, who's a rheumatology expert, and Ashley Chi, who's our malaria collaborator who runs radio cells. And we move on to Thank you very much.
You mentioned the difficulty of getting decent signals from what you do nanoparticle sensors. If you're going to be tagging something anyway, would it not be easier to do fluorescence? And what are the advantages of using your technique over, say, a quantum dot as a label?
So compared to organic fluorescent dyes, I mean, there's difficulty there with photo bleaching, handling, preparation to get very, very good signal. So quantum dots, I think, would have a more reproducible signal, but they have those dropouts, right? So they blink on and off. So if you happen to be trying to scan a cell when they blink off, you wouldn't see them at all. So it really depends, yeah, I would argue for some cell biology applications, quantum dots or fluorescent tags would be just as quick. But when you take into account trying to go for low cost point of care, nanoparticles are pretty cheap and easy to make, and they don't have sort of the handling difficulties that you have with fluorescent dyes or quantum dots.
Actually, one along the same line. So basically, the setup that we showed, I forgot the name, the Darkfield thing. So how does it compare to the normal? Because with the normal Darkfield microscope, you can see these nanoparticles pretty clearly into the view.
So before we came along, all the sort of nanoparticle folks who were doing live cell imaging, they couldn't image live cells because they had to do this transmission Darkfield. So it's a condenser that's like this big, right? If you want to have a good NA, and then you have to bring it out and sandwich it. So your microscope was really the first that could do the live cell imaging. And it's because we did Epi-illumination, right? So we didn't have to get a very narrow sample where we had to restrict it, but instead we would just have it inside of weld the cover slip.
So in transmission, we can do that?
No, we don't show live cell imaging.
Okay. And the second question I had was a table that you had, you were comparing the hemoglobin concentration using different techniques. So could you elaborate how do you calculate the hemoglobin concentration from the optical volume technique? Because it seems that you're collecting the phase images. I guess it's the assumption that there has to be an assumption there about the effectiveness of individual cells, because that's also concentration dependent.
So, yes, we do need to use that same factor, alpha, if we're actually going to determine a concentration from optical volume. but because we have the spectrum, we can hit the spectrum and figure out the amount of hemoglobin that's present there. Right, so depending on how much hemoglobin is in that area, we get a concentration. And then we take the volume that we measure, which is independent of that factor alpha, to do concentration times volume to get the total amount.
Okay, so they're on the spectrum, the concentration.
We get concentration from the spectrum, and then morphology, and we able to multiply those. And we are then free of that alpha factor.
Okay, so the phase imaging at a single wavelength, you can use the optical volume or something like that.
You can measure optical volume, but then you don't have the spectrum. So what I've seen in most phase imaging is they'll take that value at one wavelength, multiply it by that alpha, and say, some assumptions and fudge factors, and say this is the concentration. But there hasn't been a lot of studies that show, imaging of more than just a few cells and comparison across stages.
Very nice. RBC work. So, before you do machine learning, feature selection can be very important before you do machine learning. So, if you look at like geometric transform, except for the tough transform, so that you can get a better feature selection.
So I can't say we looked at a circular half transform. I mean, there's lots of things that you would look at. We did a pretty wide search, so you saw that we had a bunch of different ones. What we're going for were really things we can compute quickly on GPU, right? So, it was a multi-step operation, it was probably something that we would really look at. But it was something that you could easily do with manipulation on. That was consistent. So maximum optical path length, just look at the histogram. Right? Once you've got the histogram, it's easy to do skewness of the histogram and values. So really trying to distill it down. I'm sure there are a lot more things that you can look at.
I was intrigued. I think at some point you said you're using the gram-astronomic relationship as a variable. How does that work? Because I always thought it is very sensitive to noise, right? Because it essentially, Hilbert transform is convolved with one of the two. Do you have to regularize or?
Yeah, it is regular. Got some papers on that to share with you. I know with pyramid coroning, you're really supposed to have all of the information. We're looking over a restricted range. We make some arguments that some of that stuff just doesn't really matter very much if you're looking at things that are absorbing mostly visible. With hemoglobin, you kind of know that it's basically a broad shape with just a few distinct features in the region that you're looking at. So you can make some assumptions about how it's behaving away from where you're looking.
Extrapolate fluorescence.
Exactly. Right, so it's mostly pretty broad and flat except for sober bands.
About your phase contrast imaging, particularly the inch, I don't know if I'm cherry picking, and I apologize if the question is naive, but I thought a lot of your z-axis only went up to about 5 radians, and I'm wondering if you have ambiguity up past 2 pi, or whether you can recover that data because you have a little spectral breadth, or you have an algorithmic trick, or something like that.
No, we don't have much magic there, so we're using sort of standard unwrapping algorithms. I didn't show it today, but we come up with some clever ways of tracking more than 2 pi changes. So one approach is to use 2 wavelengths at once and make a synthetic peak wavelength out of that, which is okay. You find that the noise properties aren't great. But then if you really want to do these studies, one of the papers by Reinhardt, he actually fabricated this little plastic PDMS ramp that he would sit there. So there was no 2 pi ambiguity. You could look at the field of view, it would just sit off to the side. You could track it all the way through. And he was using this to look at how films dissolved. And there you did have this more than 2 pi changes.
Any questions?
Just thank you.